exotherm. I would say that is a two-step exotherm. But I can do more. Of those two steps, one of them is faster than the other. Right? One of those steps is faster than the other. How do I know that? Well, what you want to remember is that if I ask you, how much time does it take me, to climb a short hill versus climbing a tall hill? So if I have time on this axis and energy expenditure, the shorter the hill I'm climbing, the less time I put into climbing it. It takes a longer time to climb a long hill, a tall hill. So, climbing a short hill is faster. Less time is faster. Climbing a short hill is faster than climbing a tall hill. Right? That makes sense. In going from reactant to intermediate, I am climbing a tall hill. I am putting in that much energy. But in going from intermediate to product, the hill I'm climbing is that one. So the activation energy, remember we mentioned that term, the activation energy associated with going, in this case, from intermediate to product is much less than in going from reactant to transition state 1. If the activation energy barrier is low, the reaction of the step happens rapidly, climbing a short hill. If the activation energy barrier is large, right, then it takes more time to accumulate that energy to climb that hill. So I can go better and say this is a two-step exotherm where step 1, and I'm going to phrase this in a couple of ways. I can say step 1 is the slower step. So why am I focusing on the step that is slower? And I could have just as well said step 2 is the fastest step. But here's the deal. And you'd have met this in Gen Chem 2. If you have multiple processes that collectively lead to an event, the one process that is the slowest determines the overall rate of the event. So if the speed limit on the interstate was suddenly raised to the speed of light, but the speed limit on the ramp into Fort Smith was lowered to 1 mile per hour. If I stood at the base of the ramp and I clocked the rate at which cars enter Fort Smith, what is the rate? What's the speed? Is it the speed of light? Or is it 1 mile per hour? And the answer is, it's 1 mile per hour. There will be a bottleneck at the ramp. So the cars are moving at the speed of light, but then the rate at which they come into the city is only 1 mile per hour, so that is your bottleneck. Your bottleneck determines the overall rate of the process. So I don't really care how fast the fast steps are. What determines when I get to product is the slow step, or the slowest step, or the slower step, it depends. So the slowest step in the reaction is called the rate determining step, or some people say the rate limiting step. So that's the one I'm going to focus on. So I can say that this is a two-step exotherm, where step 1 is the slower step, or it is the rate determining step. So RDS is the accepted abbreviation for rate determining step. So I can say this is a two-step exotherm where step step 1 is the RDS. And if you ask me to write out the mechanism for how the reaction goes, I would say R goes to I, and this is the rate determining step, and then I goes to P. Okay? Let's do another one. Let's say I ask you to sketch the reaction profile diagram. So I'm going to say sketch the reaction profile diagram for a 3-step endotherm where step 2 is the RDS, or step 2 is rate limiting or rate determining. So I want to sketch a reaction profile diagram for a 3-step endotherm where step 2 is the RDS. Okay? First things first, I'm going to draw the axes as H and reaction coordinate. Again, if this question is worth 5 points, you get a half a point for putting on the axes, for labeling the axes. Okay. I know it's an endotherm. So I'm going to start here, and I'm going to end up here. And I'm going to give myself some room in the middle because I know it's 3 steps. Put a little bit lower, right? 3 steps. So if it's 3 steps, I'm going to have 3 humps. So I'm going to have hump 1. I'm going to have hump 2. Now, I have to draw hump 2 so that the number, so that the gap in hump 2 is bigger than this gap. So in fact, maybe I'll make this a little bit lower. So I'll do it like this. That's hump 1. And I'm going to make hump 2 much taller. And then I don't really care where hump 3 is. Okay? So I'm going to have reactant. And the question might also ask you to label the minima and the maximum. So I'll have reactant, I'll have transition state 1, intermediate 1, transition state 2, intermediate 2, transition state 3, and then product. Okay? Now, this is a delta H of the reaction. And it's clearly positive because HP, H of the product, is a bigger number than HR. So 10 minus 5 is going to be a positive number. So that takes you on the bit being endotherm. There are 3 humps. 1, that's 1 step, so minimum to minimum, 1 step. Minimum to minimum, 1 step. Minimum to minimum, next step. So there's 3 steps. That takes care of that. The activation energy barrier for step 1 is this number. It's called an EA1. The barrier for step 2 is that number. It's called an EA2. Usually people put a number sign on it. The barrier for step 3 is this. It's called an EA3. So of the 3 steps, step 2 has the largest activation energy barrier. It is therefore the slowest step in the reaction. It is therefore the rate determining step. It is the rate determining step. Now I'm going to make a point here. The activation energy barrier is a difference between the minimum and the minimum, between the consecutive minimum. Between the minimum and the maximum. Right? So the activation energy barrier is the gap between the minimum and the succeeding maximum. It is not the value of the maximum. So even though transition state 3 is the highest in the system, that's okay. The gap between it and the preceding minimum is actually, in this case, the lowest. This question could have just as easily have been answered with a plot that looked like this. Right? That would also have been correct. Right? I don't know whether this transition state is higher, same value, or lower value. I don't know. Frankly, I don't care. I'm not interested in the transition state energy. I'm interested in the energy gap between that transition state and its preceding minimum. That number is what is the acquisition energy barrier, is the acquisition energy. So here is EA1. Here is EA2, that's a bigger number. Here is EA3. So in this case, step 3 is the fastest. I don't really care. It was the fastest there too. So my point is the transition state energy does not determine by itself the acquisition energy for the system. It is the energy difference between the preceding minimum and the maximum, and the transition state. I will make one last point. When you sketch these curves, it is impossible for any intermediate, or for God's sake transition state, to be as stable as the product. So the intermediate energies must always be higher than the product energies. Otherwise the reaction will stop. So when you draw these, the energy of the product must be lower than the energy of the intermediates. Okay? And well, the same is true of the reactant for that matter. So you want to make sure when you're sketching them that you're aware of those idiosyncrasies. Okay. So when you're looking at reaction profile diagrams, if in reaction that's synchronous, there are no intermediates. The reaction goes in a concerted fashion, synchronous fashion from reagent to the product. When it's a multi-step reaction, it has intermediates. 2 steps, 1 intermediate, right? 2 steps, 1 intermediate. 3 steps, 2 intermediates. 4 steps, 3 intermediates, and so on. Every step has its own transition state. So the number of transition states equals the number of steps. And if you're ever asked to describe the reaction profile diagram, you will tell me how many steps, is it an endotherm, an exotherm, or thermoneutral, and which step, if any, is the rate determining step. And I say if any, because if you only have 1 step, well then that step is the rate determining step, right? I mean, it's kind of silly to speak of a rate determining step when you only have 1 step. So I'll say that again. It's silly to speak of a rate determining step when you only have 1 step, right? Okay. So we're going to change focus, and we're going to look at orbital interactions. Orbital interactions, and again, you would have met this in Gen Chem 1, so this should be familiar. And we will talk a little bit about the formation of dihydrogen in a couple of ways. So if you remember, way back in high school, you may have talked about looking at 2 hydrogen atoms, for example, coming together, and 2 electrons give you a scenario in which I have the HH bond. So these two electrons are those two electrons. So that's my dot structure, that's my dash structure. But it may also be described as the electron and the nucleus, proton of one hydrogen, overlapping, that one's bigger, overlapping with the other, well, doesn't matter, right? These two overlap, and you get something that looks like this. Two electrons are being shared, right? And we talked about this before, where the electrons are being shared. It's the mutual attraction of the nucleus for the electron pairs that holds, that constitutes the bond, right? So these are three cartoons, if you will, of what the bonding in HH looks like. But there is a more accurate, a more modern viewpoint that involves orbitals. So you remember from your Gen Chem that I can describe the hydrogen atom. So this is energy. I've got the 1s orbital. And there are, of course, no electrons in any of the 2s or whatever, right, 2p's. So hydrogen has a lone 1s electron. It has a lone 1s electron. Right? So that electron occupies the 1s orbital. So when, and the 1s orbital is spherical. So when the 1s orbital, and I'm going to put now a dot to represent the nucleus this time, not the electron. When the 1s orbital of hydrogen overlaps with the 1s orbital of another hydrogen, so we're looking now at the molecular orbital picture. Right? At the beginning, the 1s's are atomic orbitals. Right? These are atomic orbitals. Meaning that they are, or the AOs, meaning that they are localized on an individual atom only. So what I'm drawing here then is the nucleus of a hydrogen atom. That circle, which represents a sphere, around that nucleus represents the region of space, the volume of space, where there is the maximal probability of finding the electron. Now, in the real world, there would be no skin on this thing, right? Because the probability decays to 0, but it never quite reaches 0, but it approaches 0. So really, in the end, I have no boundary. There's a finite probability that the electron in this hydrogen is across the room, or it's in Tulsa, or it's on Mars. There's a non-zero probability that that's the case. It's just a very, very small probability. But if I were to sum the probabilities, 99.999% of the probability is that it's contained somewhere in that volume of space. So here are two 1s atomic orbitals. They are localized on an individual hydrogen. They overlap. And in the process, what we end up forming is two orbitals. And that's very important. There is a concept called orbital conservation, right? It's orbital conservation. And the idea is that the number of orbitals I put in must equal the number I get out. If I overlap, if I interact n orbitals, I will get n orbitals out. I must conserve the number of orbitals. So when I overlap the 1s and the 1s, two orbitals must form. Those orbitals look like this. Those orbitals look like that. I call this one the sigma star 1s, and this one the sigma 1s. Okay. Let's talk about that for a little bit. Sigma orbitals are one kind of molecular orbitals. We talk about sigma and pi's. Sigma orbitals are formed when the atomic orbitals overlap end-on. So they overlap head-on, right? Head-on, end-on, or what we say is collinear. So they're both moving along the same line. So collinear, end-on or head-on overlap is referred to as sigma. Any orbital formed by such overlap is called a sigma orbital. So really, a sigma orbital doesn't care what the types of orbitals are. It doesn't. It just cares how they approach each other. If they approach each other end-on, it's called sigma. So again, I'll write this down. It is collinear. It is end-on, or it's also called head-on. So head-on overlap or collinear overlap, right? So they're approaching on the same line. Collinear, head-on, end-on, gives rise to sigma orbitals. Because there were two of these, I must make two. What were the orbitals that formed the sigmas? Well, they were 1s. So it's called a sigma 1s, and the other one is called a sigma star 1s. Now, how are they different? I can imagine on this axis, I have energy. Here is the energy of my 1s orbitals. It's some non-zero value. Right? There's some finite energy of my orbitals. When the orbitals overlap to form the two, sigma and sigma star, one of them is significantly more stable than the initial 1s's. The other one is significantly less stable than the 1s's. And what's interesting is this gap is equal to this gap, which it must because we're conserving energy. There is a name for these two orbitals beyond the sigma 1s and sigma star 1s. This is called a bonding molecular orbital, and this one is called an anti-bonding molecular orbital. So why is that? And what does that mean? And by the way, when you see the asterisk next to the orbital, it means anti-bonding. The absence of an asterisk means you're bonding. Well, that's not quite true because you could be non-bonding. So the asterisk means you're anti-bonding. So what does that mean? Bear in mind now that these dots represent the nuclei, right? These nuclei. What is this telling me? It's telling me that these two nuclei are bathed in electron density. Because what does this skin represent? It represents that volume of space where you have the greatest probability of finding the electrons. And now there are two electrons, right? Because each 1s brought with it one electron. So where is the greatest probability of finding the electrons in this orbital? And the answer is here. Most of it is in that gap. So the bulk of the electron density then is in the internuclear gap. So So what does that mean? Well, it means two things for me. One is that the nuclei don't directly feed each other. The electrons are in the middle running interference. Right? So I don't expose one nucleus to the other because that's going to create massive repulsion. So by placing the electrons in the internuclear gap, I am minimizing repulsion. That's good for bonding. But I'm also maximizing attraction. Because think about it. Here, this nucleus feels one electron. This nucleus feels one electron. And that's good. But that nucleus essentially feels two electrons. And that nucleus essentially feels two electrons. So the attraction here is greater than it is here. The repulsion here is at a minimum. So I have maximized attraction. I have minimized repulsion. That's good for bonding. So this is a pro-bonding scenario. In other words, it's bonding. But look at the counterpart. I have placed the nuclei so that they directly are in conflict with each other. Plus and plus. I have maximized the force repulsion. There is nobody in the middle protecting that nucleus from its neighbor. So the force of attraction here will be massive. That will be anti-bonding. Plus, in terms of attraction, this electron, this nucleus, isn't surrounded by electron density. It's off the way to the side. It's not even as good as this one. Far less this. So in this scenario, there's really nothing good about it. Right? Your repulsion is huge. Your attraction isn't that good. So that would be a higher energy scenario. That is anti-bonding. So I can redraw this diagram, and I'll keep the same energy level axis. I can redraw this diagram in another way. So keeping the same energy axis, I can see here are my 1s orbitals. 1s, 1s. This is my sigma 1s, and this is my sigma star 1s. Okay? Now, these are energy levels. When the two 1s's come together and they merge to form the sigma 1s and the sigma star 1s, the 1s's are gone. Right? The original houses for the electrons have vanished. And in their stead, there now lie two new orbitals. What was once atomic orbitals, localized on the hydrogen atoms, are now molecular orbitals that encompass both nuclei. So I've gone from atomic orbitals to molecular orbitals. Well, where are the electrons now? Because they were originally housed in the 1s orbitals. Where are they now? Well, the only houses available are the sigma 1s and the sigma star 1s. So where do they go? Well, you've learned in Gen Chem the off-board principle. Electrons occupy the orbitals of lowest energy first, and then they go up. And each orbital, whether it is an atomic orbital or a molecular orbital, each orbital can hold two electrons as long as they're spin paired. So the two electrons that were once in the 1s, and let's say I said, and it doesn't matter what the spins are initially, those two electrons will occupy the 1s, the sigma 1s, but they'll spin pair. So if I asked you, what is the electron configuration of the hydrogen atom? You will tell me that is 1s1. Right? There is one there is one electron in the 1s orbital. Okay? There's one electron in the 1s orbital. If I ask you for the electron configuration of the hydrogen molecule, what would you tell me? Well, it's not 1s anything, because the molecule now deals with molecular orbitals. 1s is atomic, it's gone. So the electronic configuration, or the EC, of the hydrogen molecule is now sigma 1s with 2 electrons. In other words, it's sigma 1s 2. Right? It's sigma 1s 2. That is the electronic configuration of the hydrogen molecule. We'll go one step further. There is a term, which we've already used in class, by the way, called bond order. Right? There's a term called bond order. And the bond order, or the BO, is a measure of the amount of electron density in a bond. So I can have a bond order of 1, which is a single bond, a bond which means that 2 electrons being shared, a bond order of 2, which is a double bond, which means 4 electrons are being shared, all the way up to a bond order of 3, which means there are 6 electrons being shared, 2 electrons per bond. How do I calculate bond order? Well, if I tell you it's a CN bond, or C double bond, CN double bond, or C triple bond N, well, that's pretty easy. Bond order 1, bond order 2, bond order 3. But you know how we get that? We're going to ask, how many bond pairs of electrons do I have? How many pairs of bonding electrons? And how many pairs of anti-bonding electrons? The bond order is defined by, or defined as, the number of bond pairs of electrons minus the number of anti-bonding pairs. So for this molecule, what is my bond order? It's 1, because I've got 1 pair in the sigma 1s, minus 0, because I've got no electrons whatsoever. So that's equal to 1. Which is why we are justified in writing it as H single bond H, because the bond order is 1. It turns out, however, that there is a series of hydrogen species where the bond orders aren't exactly this. And I'm going to erase this so I can go over it with you guys. And you can rewind and so on as you need. So what we're going to do is we're going